All right, so today we're going to continue dealing with moments and rotational aspects. So specifically going to talk about couples. And so one way to create a moment is basically by having two forces that are equal and opposite, that are stretched some distance apart from each other. So if one to make something rotate, push one end up, the other end down, and that's going to make it want to rotate. If these forces are equal and opposite, there'll be no translational movement. So net force up and down will cancel out. So a couple, basically two forces acting, two equal and opposite forces acting some distance apart, causing rotation and no translation. So same magnitude, parallel lines of action. So I called this guy negative F, just meaning completely opposite direction. So essentially parallel line of action to this guy over here, separated some distance. That's going to cause some rotation, some moment. And the amount of rotation that is caused is just F times D. So whatever force is acting times the distance between them. So one thing to take note of here, there's only one F. So whatever this force is, so if there's 100 pounds pulling up to the right over here and 100 pounds pulling down to the left, equal and opposite down here, this F is just 100 pounds. It's just one of them. It's not both of them. So keep that in mind when you're doing this. And then D, obviously, the distance between the two forces. 3D case is actually the same. It's just a little more complicated geometrically, but you end up with the same answer. So again, what we can do is take these two moments. So just like before, I can look at the moment that this force F is creating around this point O, and then have this equal and opposite force called negative F take his moment also around a point O. So for this first force has some position vector RB, so RB crossed with F, and then add it to RA crossed with negative F, and then what I end up with is essentially the two vectors RB minus RA crossed with F, but vector addition or subtraction, RB minus RA is actually just this vector R between the two. And so I end up with that the moment created is just R cross F, kind of same as what we had before. So same equation we had in two-dimensional version. I had two forces, some distance R between them. F times R will give me that total moment. Obviously, this case in 3D, this will also have some other components, other directions involved, but in terms of magnitude, it's still the magnitude of F, one single F, times the magnitude of this distance between them. Another useful thing to do is to simplify. So if I have a whole bunch of forces and moments acting on some body, I'm going to simplify it into one equivalent force and one equivalent moment. So take all the forces, all the moments, add them all together, and just get one single equivalent force. The question is, how big should that force be, and how and where should it be located? And similarly for the moment. And so what I want to do is I want to take all these forces. All those forces are going to cause some translational tendency, some net force in some direction. They're also going to cause some rotational tendency. So it's going to want to rotate. It's going to cause some overall net moment in some direction. And then I want my single equivalent force to do the same thing. So it's cause the exact same translational and rotational tendencies. So the forces is kind of the easy part. I just take all my forces and add them all up, and that's my net force, and that's the resultant force that I want in this case. So it's just basically finding the net force. The moments are a bit more work. My total equivalent moment, my resultant moment around some point O. I take all the moments around that point O, if there's any moments acting on my object, and then all the moments created by all these other forces. So both moments and forces can create moments. So there's maybe some moments acting as well as some forces, and those forces are creating moments around point O. And I want to take all those, both individual moments and forces creating moments, and add all those moments together to get my total net moment or total resultant moment. So a few simple cases of this, combining parallel forces is the easiest case, and specifically combining just two parallel forces. And so obviously I have some beam here. I have some force A, capital A, pushing down at some distance little a from the left end, some force capital B pushing down at some distance little b, again from the left end. And then I'm going to replace both A and B by some new force, capital R, that does the exact same thing, both in terms of translational and rotational tendencies. So in terms of translational tendencies, what I'm going to need to have is the same overall force acting down. So overall force acting down, I have capital A and capital B. So my magnitude of R has to be that same thing, capital A plus capital B. And that takes care of the translational tendencies. In terms of rotational tendencies, what I need to have is that this new force R needs to provide the same moment that both force A and B together provide. So if I look at, say, the moment around this left-hand point, originally is capital A times little a, technically negative because technically that's going clockwise, and capital B times little b, again, technically negative because it's going clockwise, and then add those two together, and that's my total moment around this left-hand side. And so I want R times this distance x to give me the exact same moment. This guy is also going to create a negative or clockwise moment, so I'm not going to worry too much about signs. But what I want to have is that R times x equals A times A plus B times B, so that the final moment equals the original moment. And so that's kind of how this equation is derived. I take R times X, set it equal to the old moment, which is A times A plus B times B, and then just divide by that R, and that gives me my location X. So where this R new force should be located is given by that equation, essentially just balancing the old moment with the new moment. And that tells me where to put it so that the two moments are the same, so that the rotational tendency is the same. Another thing that may be useful to do is to actually move a force. So normally you're not supposed to move a force unless it's along its line of action. If you do want to move a force not along its line of action, you can actually do that. You just have to take into account what you just did. So when you do that, you're going to have to add in something to compensate for what you just did. In other words, take this illustrative example. So again, I have a beam. I have some force acting at point B, so way out at the end of it, some total distance L. I have this force F pushing down. I want to move that force to point A. And so when I do that, I'm obviously going to have to take into account the fact that I'm changing the rotational tendency of this beam. I'm not changing anything translational, because if I have a total force F pushing down at B, or a total force F pushing down at A, that's the same total force pushing down. So in terms of translational stuff, I'm fine. It's just I'm changing the moment if I move this from B to A. So I have to compensate for that. So F goes to F prime. And now I want this new F prime force to do pretty much, as I said, exactly the same as this old F force. So in terms of magnitude, it's the same. But in terms of moment, looking at the old moment, the black force, F, is at some distance L. So the total moment around point C from the black force is negative, because it's clockwise, F times L. My new red force moment around point C, again, it's going to be clockwise, so still negative. F prime, which is the same as F, times the distance x. So what I have in this case is minus Fx. This is smaller in magnitude anyway than my old force, so I have to compensate by adding in a new couple. So if I move a force, I can do that as long as I add back in a couple or a moment that compensates for the change in moment that occurs when I move that force. So now I need to figure out what is this change in moment. So from negative FL, I now only have negative Fx, but I want it to still be FL. And so if I add back in a moment, I'm going to call that M prime. that's negative F times L minus X, that's going to give me back that original moment of negative F times L, because the moment that is, if I distribute this F, I'll have my negative FL, there it is. But then I'll also have a positive F times X, but that positive F times X moment will be canceled out by this force F prime times this distance X, causing its own moment. So those two parts cancel out, and I'm left with overall from these two objects, both force and the moment, they combine together to give me a total moment of negative FL. Now that was for this one specific case with X's and L's. In general, what you need to do is add back in a moment of the force times the distance that you move it. So if I want to move a force from any point A to any other point B, I can do that as long as I add in a new moment that has a magnitude of that force times that distance that you move the force. So in this case, I move the force a total distance of L minus X. And so that's the moment I have to add it back in, a total moment of force times that distance I moved it, L minus X. Now, one thing that doesn't show up here is the fact there's a minus sign, and that really depends on where you're moving it. And so that's something you kind of have to do by inspection. Looking at over here, I moved F to the left, but that's not really what the important part is. The important part is that when I moved F from B to A, I ended up producing a smaller negative moment. So because F prime produces a smaller negative moment, I need to add back in a more negative moment, or add back in a minus sign here to give me a more negative moment overall. If I was on the left side of C, it'd be completely backwards, because moving to the left would give me a more positive moment. And so that's why you have to kind of look at it. Don't think of it left, right, up, down. You know, again, go back to forgetting that sign convention. Just look at clockwise, counterclockwise. When I moved it, did that provide a smaller moment or a bigger moment? Was that negative or was that positive? And then from there, you can figure out, okay, I need a more negative one, or I need a more positive one, or whatever it needs to be. So as a summary of the procedure we just did, any force can move. You can move it from point A, provided you add back in a moment that compensates for the fact that you moved that certain distance. The magnitude of that moment is F times the distance. And then again, the sign you have to look at in terms of which way did it go, and is it now producing a larger or smaller positive or negative moment. There's a few common systems of forces that you see a lot. One of them is a concurrent force system. What this means is I have a bunch of forces acting on an object, and if I draw all those lines of action of all those forces, they all intersect at some common point somewhere in the picture. So down here, I have all these forces, F1, F2, and F3, draw all their lines of action, and they all intersect at this point O, located on the object. It doesn't necessarily need to be located on the object. It's just a matter of these lines of actions all intersect somewhere. It doesn't matter where. Nice thing about this is that if I have a concurrent force system, if I want to find the net force, so again, want to combine all these forces into one single force acting on my object, all I need to do is find that net force. So just like I did before, all these three forces added together as vectors, and that'll give me my net resultant force. And because they intersect at point O, if I place that resultant force at point O, there'll be zero moment involved. And so this kind of is how we can reduce things to single particles, like we did a couple lectures ago. So particle equilibrium, all my forces could be placed at a single point. Kind of same thing here. I can move all these forces along their lines of action so that they all act at the single point O, and I can basically treat this object as a particle in that case. So any concurrent force system I have reduces my object to a particle. No rotation, no moment to worry about. Next, we have coplanar force systems. So these are, again, kind of like a two-dimensional force system. I only have forces in 2 dimensions, X and Y usually. And so anytime I have this scenario, it doesn't necessarily need to be X and Y, it could be any kind of plane, but it's easiest to call that plane the XY plane. So anytime this happens, my total resultant force will also lie in that same plane. And then the moment will be perpendicular to that plane. Again, since the moment is cross product of distances times forces, and all distances and forces are in the plane. So perpendicular to that is where my moments are. Again, usually called the z direction. And this guy, again, a lot of times I want to take all these forces and replace it with some single equivalent force. And that one single equivalent force has the exact same translational and rotational qualities as the original force system, however many there were. And as usual, to find that net force, just add all the forces together, find the net force. The moment, mr about some point O, is fr times d. So again, perpendicular distance and force. That's the sum of all the moments. So basically what I can do with that is I can find this distance d from point O that I can move my force, and that essentially gets rid of this moment. So we'll see a few examples of that in a few different cases later in this video. If I have two parallel forces, this equation just reduces that down to the one we had on slide 5 with the A's and B's. So graphically, what I'm talking about, again, for me, words are very hard to understand. If I see it in pictures, it makes a lot more sense. So coplanar force system, I have all these forces acting in the, I'm going to call it, again, the XY plane, in the plane of the computer screen. Don't necessarily intersect at some common point. So not necessarily some point where all the lines of action intersect, just some random forces going in random directions. But again, in the plane. Again, I can take those forces, add them all up, and find some net resultant force. And so that is my net force. That's the same, going to cause the same translational motions. Then I can also take the moment of all these forces. So there's going to be some moment around some point. Again, it doesn't really matter what point I take. I'm just taking point O. That could be in the middle, it could be in the corner, could be anywhere really. But I want to take the moment of all these forces around that point. So there's going to be some perpendicular distance from F1 to point O. And so those cause some moment. You're going to call that M1. Same thing for F2 is going to cause some moment around point O. F3 is going to cause some moment around point O. And those three added together is my total net moment around point O. So what I've essentially done is broken this down from 3 forces into a single force and a single moment. But I can do one better than that. I can actually just get rid of this moment as well by moving this force. So if I have a moment that is causing some rotation, I can cause that rotation by moving this force. So it's essentially like if I have a pencil and I just have a force pushing on my pencil at some location, at the center of mass, for example, I can balance this thing. But if I also have a moment that's going to want to twist this thing, well, I can equally do that by just moving this force over. Then moving this force over is going to want to rotate it as well. So that's basically what I'm doing here. By moving this force over some perpendicular distance, I'm essentially now causing this moment MRO by moving this force. So this force FR times this distance d is equal in magnitude to MRO. So this FR is not only now causing the translational part, it's also causing the rotational part as well. So I've essentially broken down 3 forces into one single force that does the exact same thing on my object. Another common scenario is to have a parallel force system. So instead of all the forces being in a plane, they're now all acting in the same direction, not necessarily on the same line of action. They could be spread apart, parallel distances, but all their lines of action are parallel. So they're all going down, for example, or they're all going into the board. They're all going the same direction, but just at different locations. In this case, obviously, the net resultant force is also going to go in that same direction. And I can do similar things to what I did before. I can break that down, all those forces, find some moment around some point. So now I've broken it down into some net resultant force and a moment, and then I can actually move that force a certain perpendicular distance given by actually the same equation we had before. And by moving that certain distance, I can now have that force cause a moment. So instead of having a force and a moment, I'm left with just a force that does the exact same thing as the original set of forces. So again, pictorially, I have these forces. I drew them all going up and down. Just as long as they're in the same direction, that's all that really matters, acting on this object. I drew these axes in here. These are kind of arbitrary axes. That's why I didn't actually label them X, Y, or Z or anything. All I really wanted is that one axis, in this case, the vertical axis, is in the same direction as my forces. These forces are going to cause some moment around point O, around some axis, and that's just this other axis. So the second axis going up to the right just happens to be the axis that these forces cause a moment around. Again, that's kind of completely general. I can draw that not anywhere I want, but I'm just saying this one that I drew here happens to be that axis. And so I can take these three forces and add them all together. That gives me the net resultant force, again, going in the same direction, so either up or down. I just drew it going down. And then these guys also cause some moment around point O. I'm going to say that goes in this direction. And now what I want to do is get rid of this moment by moving this force. And so I do that by moving it in the perpendicular direction. And so that's where my third axis comes in. So this direction that this force gets moved is perpendicular to both the force, the net force, and the net moment. If you think about the right-hand rule, the way I've drawn this, MRO goes up to the right. So that's going to cause a rotation downwards if I'm looking over on this side, as opposed to this side back here. So this plate's going to want to rotate around this axis with the back side coming up, the front side going down. So because I have a force in the downward direction, I want to move that force down or out, whatever you want to call it, in this direction here. So that way this force is now causing that moment that's equivalent to MRO based on that distance d. So again, d times FR is the magnitude of MRO. And that way I have the translational qualities because this net force is all these three forces added together. And I have the rotational qualities because this force times that distance is that net moment. And then last thing is reduction to a wrench. So if you have a general three-dimensional system, not necessarily coplanar, not necessarily parallel, not necessarily any of those special cases, we can't specifically break it down into just one single force. So before, I could take all my forces, turn them into a force in a moment, and then turn that into a single force. For a general 3D system, you can't always do that. The best you can do is turn it into a force and a moment that lie on the same axis and act at the same point. So the way I want to do that is because I want my force and my moment to lie on the same line of action, essentially they're parallel to each other. So I want to find the parallel component of the moment that's being created. So to find a parallel component of a moment, I just take the entire moment and dot product it with the direction I want. In this case, the direction I want is the resultant force direction. So unit vector EFR, the direction of my resultant force. Take the dot product with the overall moment, and that gives me the parallel component of that moment. So parallel with respect to the resultant force. And basically I can take that resultant moment, break it down into parallel and perpendicular components. So if I do that, the perpendicular component is the total moment, subtract away the parallel moment, and that gives me the perpendicular component. And I can remove this perpendicular component by doing a very similar thing to what we did the previous two cases. So find some distance d to move it in the perpendicular direction, perpendicular to both the perpendicular moment and the force. And then that way my force will cause that perpendicular moment. And so I can get rid of it, but I'll still have to keep the parallel component. So I'll end up with a force and a parallel moment as opposed to just a force in this case. And that's called a wrench or a screw. And it's called a wrench or a screw because if you think about a wrench or a screw, if screwdriver, for example, you put the screwdriver into the screw and you push down on it, so there's a net force, and you also twist it, so there's also a moment around that same axis. So you have basically a parallel moment and a force acting on the same line in the same direction. So that's why it's called a wrench or a screw. So again, pictorially, what we have, I didn't actually start with the first one, so before we get to this, there should be another one out here, with just a whole bunch of random forces acting on it, so not necessarily parallel, coplanar, whatever, they're just a whole bunch of forces going a whole bunch of different directions. We want to turn that into sum total net resultant force, so take all those forces, whatever they are, add them all together as vectors, gives me this total net force, FR. And then all those forces are going to cause some total net moment. So take the moment of each force around point O and add all those together to give me a total net moment, MRO in this case. And again, here I have these arbitrary axes on this object. So I just pick the vertical one to line up with the net force. And then I have this MRO going off in some somewhat general direction because they don't necessarily lie on the axis like they did before. It is going to be at some angle, or could possibly be at some angle. But then the next thing I want to do is, once I have my net force and net moment, is to break down this moment into its parallel and perpendicular components. So if I break that down into parallel and perpendicular components, I don't really need that guy anymore. So these two moments add up to that net moment. And then what I can do, like I did before, I can get rid of this perpendicular part of the moment by moving my net force a certain direction. So this distance d times this m perpendicular is the, this distance d times this force Fr is equal to m perpendicular. In this case, because my force is going up instead of down like it was last time, I need to move it the opposite direction because, again, right-hand rule, this m perpendicular makes this backside go up. So I want this force to also make this backside go up. So move him in that direction, again, perpendicular to both the force and m perpendicular. And then m parallel. Moments, unlike forces, you can actually move moments. So moments don't necessarily need to move just along their line of action. There's something that are called free vectors. So that means I can actually move it to any point I want, and it's going to have the same effect. The only key here is that this moment is going in the vertical direction. It's still going in that vertical direction. Moments are basically rotations. So if I have a rotation around a vertical axis, it doesn't really matter where that axis is. It's still rotating in the same orientation. So that's why I can move it. So once I've moved FR over to this new point P, I'm also free to move M parallel over to this point P. And so there's my wrench or screw, FR and M moment, same line of action at the same point, single force, single moment. So that is the end of moments. Next class, we have to deal with some distributed loads. So everything we've dealt with so far has been just a point source. We'll deal with how we we'll find out how to deal with things that are spread out over a certain area next class. Then we'll get into the real fun of this course, which is rigid body equilibrium. So equilibrium taking into account rotations.